Welcome to our next lecture in the series on condensed matter theory. In this video I want to talk about an example where we find surface states on a cubic lattice where we have a basis of an S and a P shell. So we have four orbitals, the S, the Px, the Py and the Pz, and we'll have a simple cubic lattice structure with nearest neighbor hopping. And we'll make a surface in the 0, 0, 1 direction. So if we look in real space, then we have in the x and in the y direction an infinite lattice, and the z direction a semi-infinite lattice. So we can transform to Fourier space in the x and the y direction, and we'll work in real space in the z direction. Now, when we have a basis of S and P, we have to think about the hopping parameters, and very important about the sign of the hopping parameters. And for this we will use the Slater parameterization. And you'll find a link up there to a video where we introduce this. But if we have two s orbitals and we look at the angular dependence, so not at the radial dependence, then the angular dependence is a sphere, the wave function is positive in all directions, and therefore the hopping parameter is smaller than 0. If you look at the interaction between an S and a P orbital, and what we plot here is the radial dependence of the wave function, then you'll find that the P orbital changes sign between the plus z and the minus z direction for a pz orbital, and therefore you have now a plus slope pointing towards a minus slope, and that changes the sign of the hopping integral, and the hopping between two P orbitals is positive. The hopping between a P and an s orbital is again a plus slope pointing towards a minus slope, and therefore also sp sigma is larger than 0. And for p orbitals you can also make a pi bond where the orbitals point away from each other. Now formally this should be smaller than 0, but because these orbitals don't point towards each other, the hopping is much smaller, and we will neglect it here. The idea is not to get a quantitative description of a certain material, but I want to show you the qualitative features that we can get when we look at surface states with more than one band per unit cell. So with this we can build our Hamiltonian in real space, and we now want to transform this into an Hamiltonian in K-space, and for that we can use a Fourier transform. We did this before for a one-dimensional lattice with a basis of an S and a P orbital. Again, the link is somewhere there, and the result I'm just going to write down: the Hamiltonian in K-space on a basis of log waves Px, K, Py, K, Pz, and Ks is given by, for the Px orbital, the on-site energy epsilon P to Pp sigma cosine Kx, and then the on-site energy for the Py orbital epsilon P plus 2 Pp sigma cosine Ky, and the on-site energy for the Z orbital epsilon P plus 2 Pp sigma cosine Kz. And then for the S orbital, the on-site energy is epsilon S plus 2 SS sigma cosine kx plus cosine ky plus cosine kz. The s orbital can hop in all three directions. The hopping of the p orbital is directional because of the lobes that the p orbital has. There is no interaction between the p orbitals because we set pp pi to 0. But there is a direct interaction between the p and the s orbitals. Now the hopping between an s orbital, if I hop from s to p to the right, you hop from a plus lobe to a minus lobe. But if you hop from a p orbital or from an s orbital to a p orbital in the minus direction, you hop from a plus lobe to a plus lobe. So you have a different sign for hopping to the right and from to the left. So you get e to the ikx minus e to the minus ikx, and that gives rise to a sign dependence on the hopping matrix elements instead of a cosine dependence where the hopping to the right is equal in sign to the hopping to the left. And our Hamiltonian is Hermitian, so this is plus 2i sp sigma sine kx 2i sp sigma sine ky 2i sp sigma sine kz. And that is our Hamiltonian in k-space. Now if we neglect first of all the interaction between the s and the p orbitals, our Hamiltonian is diagonal. So we can immediately plot the bulk band structure. And we'll do this first of all for the s band. And in the Brillouin zone, we're going to walk from the corner to gamma, to x, to m, back to gamma. From R to gamma we have the full dispersion where both the x, y and the z direction disperse. So we have a cosine dispersion with a width of 12 SS sigma. Then from gamma to x we have a dispersion of 4 SS sigma. From x to m we have a dispersion of 4 SS sigma. I have small 4s and big 12s, and then we have a dispersion of 8 SS sigma. When we go back from m to gamma, we can also look at the p bulk band structure. And again we go from R to gamma to x to m to gamma. From R to gamma we have a cosine-like dispersion, and note that here the minimum is at gamma because SS sigma is smaller than 0. Here the maximum is at gamma because pp sigma is larger than 0. And from R to gamma the px, the py and the pz orbital are all degenerate. Then at gamma we move from gamma to x, and in that case the px orbital is dispersing. That's a beautiful cosine function that I made here. And the py and the pz orbital do not disperse. Then from x to m we change ky, so the py orbital is dispersing, whereas the px and the pz band do not disperse. And then from m to gamma we change from pi over a 0 to 0, 0, 0. So both the x and the y orbital disperse, and the z orbital doesn't. And we're back to a single band at gamma. Now instead of looking at the bulk band structure, we can also look at the surface projected bands. Here the R point becomes an M bar, gamma becomes gamma bar, X becomes X bar, M becomes M bar, gamma is gamma bar. R, of course, is pi over A, pi over A, pi over A, but at the surface the Z direction is basically integrated over. So if we look at our bands, we have here a dispersion of 8 SS sigma, both for Kz is 0 and Kz is equal to pi over A, and all states in between are allowed. Then from gamma to X we have a dispersion of 4 SS sigma, both at Kz is 0 and Kz is pi over A. And from X to M we again have a dispersion of 4 SS sigma. And from M bar to gamma bar we disperse completely back to the minimum at gamma. So that's the S-band. Surface projected states. And those energies you will find eigenstates that can disperse into the continuum. Now for the p-bands, in the cubic bulk, px, py and pz are all equivalent. At the surface we'll make a distinction between the px and the py bands and the pz band. Gamma bar, X bar, M bar, gamma bar, and we start at M bar. So now the px and the py orbitals have no dispersion in the z direction. We are neglecting pp pi. So they become well-defined single states. The px and the py band both have a cosine-like dispersion when you move in the 1,1 direction. Then from gamma to x, the py band doesn't disperse, but the px band does. From x to m, the px band doesn't disperse, but the py band does. And from m bar back to gamma bar, we have a cosine-like dispersion of both of the bands simultaneously. So these are just the same as what we have here, except that the pz band is missing. For the pz band, we should realize that we have no dispersion in the x and the y direction and only in the z direction. So we find no dispersion and we integrate over the z dispersion to get the surface projected bands. So these are the surface projected bands of the pz orbital. Now, what we want to do is have both of these bands in a similar energy window and then add an interaction between them and see how these bands evolve for either different strengths of that interaction or different energies between them. And for this we can of course happily use computers. We have analytical equations for them, they're just not nice, and I don't want to diagonalize all this and look at the equations, that become too long. So let's have a look what the computer tells us what the solutions are. And in the first plot that we have here, we have the S bands above the P bands, and we introduced an interaction between the two of them. And what you see is that they are reasonably similar to the plots that I made by hand, except that between R and gamma, the px, py and pz bands in my plots were degenerate, whereas the computer tells you that there is a difference between them. And the reason is that I neglected the interaction between them, whereas in the computer I turned them on. And if you take a linear combination of px plus py plus pz, then on the line in the 1,1,1 direction, that orbital interacts with the s orbital, and you get a hybridization and a level repulsion such that these levels split and the other two remain at the original energies. And of course that interaction also slightly then changes the cosine-like dispersions that we had before. But then again, my plots weren't perfectly cosine-like either. Now we go to the next plot where I reduced the difference in on-site energy. And you see that when the S-band and the P-band become at the same energy in gamma, then they are staying at the same energy there. It's important to realize that the interaction between the S-band and the P-band always has a prefactor that is the sign of the K vector. So when the K vector is either 0 or pi over A, that interaction is going to be 0, and that happens exactly at the high symmetry point, so the R, gamma, X, or M point in the Brillouin zone. Now once the energy difference is even smaller, such that the band crosses, then you see that in the window, again from R to gamma, you start at the R point with the S band on top, then you move towards gamma. At gamma, the S character is completely changed into P character. And you now also see that we plot the partial character in terms of colors. So the red S band changes into a blue P band at gamma. Then, because the S band can only interact with a single P band, you can move from gamma back to R by a P band. And then from R you can move to gamma by a band that starts as a P band and then changes into an S band when you're at gamma. So the moment that the bottom of the S band is below the top of the P band, and at the same time the top of the S band is above the bottom of the P band, so these two bands overlap if you turn off your interaction, at that point there is no gap in the spectrum between those bands anymore. So if you have partly filled S or P bands, then they will always be metallic on a cubic lattice. And actually that is true in general if you have a single orbital per unit cell with an S and a P band and they overlap in a cubic lattice. That system is going to be metallic, there is no gap opening. There are different way outs. You either put more than one atom per unit cell, which is diamond, or graphene, gallium arsenide, sorry. Or you make non-cubic distortions. For the later, actually, I don't know an example. The third way to get gaps is to add spin-orbit coupling, and that will come later in the lecture when we discuss topological states. So good so far. Then we can of course now lower the energy of the S band until it's below the P band, and then of course there is a gap between them because you're just below them. We can also look at the surface projected bands as well as calculating the true surface bands. And in the plot that you see here, we calculated both the surface projected bands on the top as well as the surface state in the bottom. And you see that for the surface state you get additional eigenstates, so bound surface states, inside the hybridization caps that form due to the interaction between the S and the P band that we have for the surface. Now these states are truly bound states without the need to add any surface potential in the system. If you make the interaction between the S and the P band even bigger, the hybridization gaps become even bigger, and those surface states remain and are clearly visible. So, in order to prove that you have surface states or not, we can jump back to things that we discussed in the previous video. And we have our surface Green's function of a semi-infinite system at 0, 0. So you create a particle in the top layer and you remove it from the top layer, and I'm suppressing here the kx and ky indices. And with the use of Dyson equation we can express this as the local Green's function of an infinite lattice plus the Green's function of an infinite lattice where you move one lattice side. And now I'm going to take matrix products, because my Green's function here is either the creation of a px, py or pz orbital or an s orbital, so these are all 4x4 matrices. and 1 minus the hopping that I have between the nearest neighbor, which is the hopping that you exactly removed to go from an infinite lattice to a surface, and then G0 locally. And this still multiplied with the Hamiltonian where you hop one side and the local Green's function. Now you get an additional pole. When the denominator here, so 1 minus the hopping Hamiltonian between the nearest neighbors in the z direction, G0, 0, 0, omega, is singular. Now for the Hamiltonians that we have here, you can in principle work this out. The equations are nasty and long, but you can show that indeed for this model this becomes singular, but actually we know this because our numerics already showed us that this becomes singular and we have this additional surface states in there. It's bidirectional. If you get a surface state, this is singular. If this is singular, you get a surface state. So indeed, we get additional surface states in these kind of type of materials. Not because we have additional surface potentials, but just because the breaking of the translation symmetry in one spatial direction is such a large perturbation that you can't work perturbatively anymore, and that you get additional eigenstates at new energies. We will come back to this model when we discuss topological phases and topological surface states. But then we need spin-orbit coupling. So before I will do that, I will make a detour and talk about the Dirac equation and relativistic effects in solids. So that's where we'll go. Thank you very much for your attention. Stay healthy, and we see each other later.